Hello, my name is Oleksii Vodka, and today I am going to speak about data-driven modeling of the L surface in heterogeneous microstructure using computer science method. Today we are going to speak about bridging the gap between microstructure physics and microscopic mechanical properties using modern computational pipelines. Classical phenomenological methods like von Mises or Tresca are built on the assumption of material isotropy. However, they fail to account the intrinsic structural complexity and the isotropy of real polycrystalline materials. Our approach transitions from grid constructive equation to simulation-based data, explicitly incorporating grain orientation and local plastic mechanism. The objective of our work is to develop the automated software pipelines and to identify the actual yield surface of heterogeneous system. This involves four main tasks: creating the workflow from voxel generation to finite element analysis, formatting a methodology for Schmidt factor identification, reconstructing the boundary surfaces in stress space, and validating the results against the classical criteria. To do this, we developed the automated computational workflow with MATVIS 3D and voxel generation, formulate methodology for identifying the probabilistic characteristic of Schmidt factor, perform algorithm reconstruction of yield surface, and conduct statistical validation and analysis. Our framework uses MATVIS 3D, which employs several automata and Moore neighborhood analysis to simulate voxel-based crystallization. These voxels are then automatically converted into hexadral elements of high precision via in ANSYS. We use Oleh angles to ensure that our principal strain trajectories cover the full spectrum of stress states from uniaxial tension to pure shear. On the left of our slide you can see the microstructure of polycrystalline material generated by MATVIS 3D, and after that this microstructure with loading conditions export to ANSYS software, perform the calculations, and back the results, and you can see the visualization of stress state of different types of loading in imported the strain again to MATVIS 3D software on the right of our slide. Core principles of our framework based on the fair data principles. All results including geometry and boundary condition are stored in HDF5 format. The data flow moves from the microstructure generation to a step processors that handle tensor recovery from Mises criteria calculation and Schmidt factor analysis to find the maximum scaling for yield points. On the left side of the slide you can see that the internal structure of HDF5 format and total pipeline that you can see consists from the MATVIS 3D microstructure generator. We use ANSYS software to estimate the stress state and collect the geometry and the stress together with the HDF5 dataset. After that we use step processor and post processor which define the config type and uses all this data and depend on the settings recover the temperature recovery and Schmidt factor of Mises criterion, calculate the eigenvalues and find the max scaling to find the yield criteria. And this results as analytical represented probabilical density function of yield criteria back to the visual models, and we get the 3D visualization of yield surface and statistics, descriptive statistics of this surface. The computing core algorithm is based on full vectorization of NumPy to eliminate slow iterative loops, a key innovation in our Eigen-tracking algorithm. Without it, sorting eigenvalues can use chaotic 180 degrees axis jumps. We introduce new algorithm for stabilization method, use the correlation matrix analysis to ensure a continuous and smooth principal axis trajectories during the loading. At the macro level, plastic deformation occurs via slip along crystallographic planes. According to Smith's law, sleep activates when the resolved shear stress reaches the critical value. Our software calculates the spatial orientation via LL angles and performs a tensor rotation to local grain axis to identify the dominant sleep system and potential 12 sleep system for BCC crystals. On the visualization you can see the atoms and the possible sleep planes when the atoms click on one atom position and introduce the same such as yield behavior of microscopic objectives. To implement this algorithm, we use the next approach. We got the input stresses here and global matrix orientation and Euler angles of local coordinate system. We calculate the rotation matrix to the predefined coordinate system, perform the tensor coordinate system rotation as mentioned as RT sigma globe multiplied by R, and assume that I from 1 to number of sleep coordinate system. We calculate the Schmidt factor for each coordinate system, and after that when we define this for all coordinate system, we find the maximum stress on each direction and use this to check is this reached the critical values or not. If reached, we can assume that they get a plastical behavior, or if not, it's elastic behavior and the yield stress not reached here. This data used to perform the building of smooth kernel density estimation to obtain the probability density function. To transform a discrete point cloud into continuous surface, we apply kernel density estimation. We use Silverman rule to adapt the bandwidth to the data destiny automatically, and this allows to calculate the marginal densities along the specific loading direction to identify the physical yield limit without prediction functions. You can see the ideal visualization. It's not real data here. And also to perform the validation and statistics, we plot histograms on von Mises stress distribution. So the load step on the different loading here, you can see that some difference between the yield limit is should be near the 300 MPa, but the mean gives 270 MPa here. And after that, we plot the stress distribution for components of this tensor. It's sigma xx, sigma yy, and sigma xy to show that the different probabilities density for different directions. It's all directions together. It's not specify one direction, so it's just all whole data set visualization just to see what we get in whole data. But we need to check the directions to understood or loading trajectory to understand which part of this loading of this distribution will be implemented. And to understand this, we build the directional for a standard directional test like uniaxial test, and we introduce for x uniaxial and y uniaxial direction, and we got symmetrical, and our value is near to the analytical value of 300 MPa, and it's good for testing purposes and gives us so low errors here. And to perform other direction, we introduce the biaxial tension like xy, pure shear for xy, sigma xy direction, and biaxial sigma x and sigma y. And you can see the difference between two axial and shear behavior here. And the same we introduce for mixed tension and shear direction, and biaxial and shear xy and xy direction here. All histograms looks like near Gaussian distribution. And in conclusion, we have developed the mathematical stable tensor core of Eigen-tracking and KDE-based pipelines that eliminates the need of priority yield function. Our fair compliant dataset available on the Nodo site and providing the foundation for integrating deep learning and neural networks into computational material mechanics. So I'm happy to answer your questions. Please write me on the contacts that should be below on this video, and I will answer your questions anytime. Thank you for attention. See you.